We're going to go ahead and go through circular motion now. To start this off, we need to kind of change the way we measure things. So far we've measured everything in degrees, but now we're going to switch over to radians, a little different from degrees. If you haven't had any experience with this, then I'm going to kind of give you the quick run through of it, not a super comprehensive thing, but just a basic rundown what it is, and then you kind of do some practice with it and you'll get used to it. If it were up to me, I think we'd get rid of all degrees and go just to radians, because it's almost a system that's kind of just given to us from math, whereas degrees kind of just arbitrarily chose 360 degrees, that's all the way around a circle, whereas with the radians we use it based off of the circle itself. So the basic idea is we have a circle and it has a radius of 1, r equals 1, and what we're going to do is we can go all the way around this circle, and if we do, we would say that we walked 2 pi distance around the circle, because circumference of a circle is 2 pi r, and in this case r is 1, so we just walked 2 pi. And then we could say stuff like if we walked, say, 3/4 of the way around the circle. So we walked around the circle 3/4 of the way, and that would be 3/4 of 2 pi, right? So that's just 6 pi over 4, or 3 pi over 2. And that would be how far we walked around that way. And then if we walked halfway around the circle, we could walk around halfway around the circle or something like that. And this would be where, and it would be half of 2 pi, which would just be pi. And we could walk 1/4 of the way around the circle like this, just walk around the circle 1/4 of the way and get to there. And then that would be just 1/4 of that, which would be 2 pi over 4, or just pi over 2. And then we could do other things too. You could come in and do, say, we could walk 1/8 of the way around, something like that. And we'd have something else. You can walk 3/8 of the way, all kinds of different things. You can go and just count how far, what fraction of the whole 2 pi you walk around it. And what we can then think of is we can do all kinds of different angles, like maybe you did here, this would be a 1/6, right? That would be pi over 3, would be a 1/6 of it, a 1/6 of 2 pi. It could be that little angle there. This could be 2/6, which would be what? 2/6 would be not 2/6, it'd be 2/3, 2 pi over 3. Yeah, and then just so on and so forth. Go around, do different angles. 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, just different fractions. I'm walking in thirds. 6 pi over 3, we're back to 2 pi. But anyway, I'm basically mapping out a lot of the unit circle, because when you calculate this degrees, walking that far around, we would have walked, I drew this little line here, this angle would be 60 degrees, and we'd have all these different angle measurements. So if you look basically and walk, and you look at how far around you walk, and then you look over at the center of the circle, let me get rid of that a little bit there, you can then look and say, all right, well, how far, how much of an angle have I walked through? So say at that pi over 3, I'd look, and I'd say, all right, I walked around to pi over 3, that's actually equivalent to 60 degrees. But what we're going to do is call it pi over 3 radians rather than 60 degrees. And I walked to this pi over 2. Well, that's a 90 degrees. That's a 90-degree angle. I walked all the way around to pi. Well, you can see that's 180 degrees, right? And I walk all the way around, that's 360 degrees. So as far as finding the equivalent there, we can basically use this as a measurement of angle. And we can do this also for circles that are bigger, because if we go to, let's say we zoom way out. So here's our unit circle, right? This is our r equals 1. What if we have some bigger circle out here? Well, all you have to do is walk around the unit circle some distance, we get some angle, and then just extend that line out. So let's say this was that 60 degrees here. That'd be 60 degrees here. It'd be pi over 3. That's the distance we walked around the unit circle. And if we walk that far around the unit circle and then trot our way out here, then we would just also go ahead and call this angle pi over 3. So it's basically just telling you, fractions of how far around a unit circle you went, and we're calling that an angle and just extending it out. If we walked around to 3 pi over 2, right? So we walked around to here, we could extend that out and find out that that's this whole way around is 270 degrees, right? So that's 270 degrees. But on our unit circle, we would have walked 3 pi over 2. So it's 3 pi over 2. We're basically just extending these lengths around the unit circle out and treating them like angle measurements, okay? And then it's more natural because going all the way around a circle is just 2 pi. It's basically take the circle you've got, make r equal 1, and then just take the fraction of how far around the unit circle it went. This also makes converting between the two pretty easily. Remember, whenever you're converting, you just multiply by 1. So all you have to do is come up with a way to get the number 1. So like, let's say I wanted to convert 60 degrees into radians. What you want to do is put something with degrees on the bottom and something with radians on the top. And then you want to make sure this stays 1. And then the choices are up to you. If you remember that halfway around the circle is pi, and a halfway around a circle is 180 degrees. You could put pi here and 180 degrees here. If you didn't remember that, you could also maybe remember that it was, or you could put 2 pi radians over 360 degrees, whatever the equivalent is, and you'll get your degrees, and your degrees cancel out, and you'll end up with the same answer either way. And the same thing going back and forth. If I told you you had, say, 3 pi over 2 radians, and radians not a real unit, so I'm not even going to write it. We kind of write it sometimes to help us, but it doesn't technically count as a real unit since it's just a ratio or a fraction of a circle. Right? It's just a we call it radians, but really it's just a fraction or a percent of a way around a circle. So it's basically dimensionless, but we can write it in there to help us with the unit conversions. So it's 3 pi over 2, and we just do the opposite. This would be, I need degrees on the top, and I need radians on the bottom, and we need this to equal 1. So again, I could put 360 here and 2 pi here, or 180 degrees up here and pi radians here, or anything else I want. As long as the two are equivalent, I could put 60 degrees here and pi over 3 radians here, and so on and so forth. Okay? Now, the advantages to this is, I know if you hadn't been brought up with degrees and instead you were brought up with radians, you'd be sitting there thinking the opposite of what you're thinking now, because if it's your first time really learning about radians, you're probably thinking, oh my gosh, why do I have to do this radians? It's so much more difficult. 360 degrees, that's easy. Well, that's just because you're used to 360 degrees. If you were brought up with radians and I was sitting here, and you got used to radians, and I was sitting here trying to convince you to use degrees, you'd be sitting here thinking, well, why do I have to use degrees? Radians makes sense and degrees doesn't make sense. And that's basically where you sit. It's just what you're used to. So if you get used to radians, you're going to like them a lot better. And one example of how you can like it a lot better, they're easier to work with mathematically. It's already set in there, but it also helps us to figure out arc length a lot better, a lot more easily. Arc length, how far around the circle you went. So back here, we were saying that radians was a fraction of what distance you went around a whole circle. Well, if we just add that r back in and say it's not 1, we can basically figure out what our distance was around the circle. So let's say I went pi over 3 out of 2 pi. I went pi over 3 around a circle. If I just multiply that back by the radius, so the radius here was a 1, if I multiply that by the radius, say the radius is 2, what's it going to do? It's going to take whatever circumference distance I had right there, right? And it's going to double it back out, and it's going to put it out at the actual length you would walk around a circle with a radius of 2. And the same thing with 3. If we had a radius of 3, you'd multiply it by 3. And so it becomes very simple to calculate arc length. So I'm just going to write arc length as a capital L for the moment. Sometimes it's a lowercase l or whatever. So L equals, and then it's very easy, r, the radius of a circle, times theta, and theta must be in radians. Must be. Okay, must be in radians. Because if you just do r times 360, it doesn't work. But here, I mean, look at this. If I say you went 2 pi around a circle, how far did you walk? It'd be 2 pi times r. Well, that would just be all the way around the circle, because 2 pi radians is all the way around the circle. And then so you would have walked the circumference, and you get back 2 pi times r. If I say you walked pi radians around the circle, then it would be pi times r, which is exactly half a circle, which is half of the 2 pi r. So no matter what you do, this just basically scales, right? So it's a good little relation to remember there. Okay, so now we had our quick crash course in radians. Let's go on. What we're doing now, this stuff with circular motion, we're going to need to be working in radians a lot of the time. So let's go ahead and move on to just back to actual circular motion. So let's actually get into that now that we've got our radians out of the way. Essentially, as we talked about before, this circular motion is basically just the projection of simple harmonic motion. Okay, that's really what it is. The same equations apply. It's just that we basically have, we have both when something's going in a circular path like this, we have a simple harmonic motion occurring in the x-axis and a simple harmonic motion occurring in the y-axis both ways. So if we project the circular motion down, we get this circular motion as it goes back and forth this way, and then of course if we project it over this way, we have a circular motion going that way, and then it's just a combination of the two, and you end up getting basically circular motion. It's like two simple harmonics put together that are perpendicular to each other, and you could imagine if we had two simple harmonics perpendicular to each other, you would end up with something going in circular motion. Okay, that means we're gonna essentially still have a lot of the same properties. Like we'll still have a period, we'll still have a frequency, and they have the same meanings, and they have the same relation. You know that frequency is 1 over the period, and vice versa. They're just reciprocals of each other. But here period is the time it takes to complete a cycle, so that's the time it takes for it to go all the way around once. Frequency is just a reciprocal of that, so those are both still there. We can define a few things, such as when we do things linearly, we have a displacement. What we're going to have now is an angular displacement. And that, of course, is just going to be delta theta. That's just going to be our angle, the angle that you traversed. We'll have an angular, so I'm going to shorthand it, an angular velocity. All right, this is the rotational equivalent of regular velocity, and that will represent with omega, the Greek letter omega, not a W, but an omega. And then there's also angular acceleration, which we're not really going to talk too much about right this moment, but we will maybe later here. And so that is alpha, the Greek letter alpha. And we can do a little chart here that shows us the relationships between them. So over here we'll do like the linear version, and then we'll do the angular version, and then their relationship. How are they related? I had to squish the word relationship in there. And so linearly we had displacement, angularly we have delta theta, and their relationship is pretty simple. It is simply that delta x, which would be, in this case, our arc length, would be the distance you traveled around the circle. We already did this above, r delta theta. Pretty simple. Linearly, we had velocity. Now we have angular velocity, and they are related very similarly. If you look, you've got, we could say that, velocity is displacement over time, and similarly, omega is angular displacement over time. And angular displacement over time, if we wanted to get back to velocity, well, to make this delta x on the top instead, to make this look like that, we'd multiply this by r, and then this by r, and we'd be back to having velocity. So pretty simple that the relationship's just going to carry on over, that v is equal to omega r. We can have linear acceleration, right? Acceleration, change in velocity over time. Angular acceleration is change in angular velocity or angular speed over time. So that's angular velocity or slash speed, I guess I should write in there. And so this is our alpha, and how are they related? Same thing. Multiply this by r, and we've got delta v on the top. Delta v over t is a, so this is just change in angular velocity times r. And you may be thinking, oh, all the relationships are just times r. Well, no, it's all got to do with r, but not every relationship going from linear to angular is just as easy as multiply by r. You may have noticed that the equations for these were just simply substitutes. So I just took out the linear version and replaced it with the angular version. Here, acceleration became alpha, v became omega. And actually that's true of any of the linear equations you know. So if you, this is a little extra, but like say for example you had delta x equals 1/2 at squared plus vit, that would just become, start swapping it out. What's delta x? Delta theta. 1/2 acceleration becomes alpha, angular acceleration. Time is no angular version of time, plus, instead of initial velocity, initial angular velocity times time. And that's true for any of the other kinematics or any other thing. And you'll find, and I'm going to go ahead and kind of complete this a little bit, there's other relationships too. So like linearly, I'm going to put a little line here because this is extra stuff. We may have to note later, but at the moment it's a little extra. So for example, there's momentum, and then there's angular momentum, and these equal each other as r cross p. That's a cross product because these are vectors. I don't know if you know that or not. And then there's that. There's mass. Even mass has a rotational version in its moment of inertia. And I equals the sum of mr squareds, and this is actually what's called a tensor. It changes by different axes and everything like that, but this is its resistance to change of its linear motion. This is its resistance to change to its circular motion. Even force has torque, and torque is related to this is F cross D or L cross V, so lever arm cross the force. And you don't need to know what cross products are, but these are all vectors, and this is a pseudo vector. Don't even need to know what that is just yet, but anyway, we get these kind of things that come on here extra, and then any equations you know, they still go. So like F equals ma, linear equation, you can make a rotational version, go torque equals I alpha. And that equation is perfectly valid and works. Okay, it's the F equals ma of rotational stuff. Just a little heads up as you go into your future of doing circular motions, as long as you know the linear version of whatever angular thing you're doing, you just swap out these things. You know, any purely linear equation you have, you just swap it over and you get an angular version that works for the angular situation. So there's not a lot to teach you about the angulars, as long as you know what the corresponding angular stuff is. The math and all the setting it up works just the same. Okay, so let's define one last thing: uniform circular motion. Uniform circular motion. And I'm not going to write this whole definition out, and I'm probably going to refer to it in the future as u.c.m. But this is essentially just motion going in a circle with no angular acceleration. So a constant angular velocity and therefore a constant tangential velocity. And we'll talk about what tangential velocity is in just a minute. Okay, so that uniform circular motion, you need to know that and have that defined. Okay, so let's go ahead and talk about centripetal acceleration. And now I said this was up here. Remember, this is circular motion. I'm going to write a little something out. Circular motion with constant angular velocity. So that's angular velocity. So it's a constant angular velocity. But constant angular velocity does not mean constant linear velocity. Doesn't mean that. And so that doesn't mean no acceleration. And in fact, you cannot go in circular motion without accelerating, right? Because remember, acceleration is a change in velocity, and velocity is a vector with a direction. And if you are going in a circular path, you are constantly changing direction. If you're changing direction, you are accelerating. So all uniform circular motion has centripetal acceleration. It's what this is called. You may have also heard of centrifugal acceleration or centrifugal force with an F. That's not a real thing we don't think of anymore, thanks to Einstein. I'll explain that in a few minutes. But right now we're worried about this centripetal acceleration. And basically it's the acceleration of an object that's undergoing uniform circular motion. Okay? What I mean by that is if something is going in circular motion, right, here we're going to go ahead and define the tangential velocity. So we've got a velocity of an object. If we look at it at just one moment in time, it has a velocity pointed out tangent to it, right? And that's the velocity tangent. That's the tangential velocity. It's tangent to the circular path, right? This is the center of our circle. But a moment later, just a moment later, it's going to turn, right? It gets to its next little spot, and it turns. And now it has a new tangential velocity. So it's like an instantaneous velocity, a velocity at one moment. And look at how it changed. It changed by rotating. It was pointed this way, then it rotated. And look what it rotated toward. It rotated right towards this center. So it turns out that this centripetal acceleration, it's called this centripetal because it's like a center-seeking acceleration. This thing is trying to go towards the center. So the acceleration is pointed toward the center. It's at a right angle to the tangential velocity, which causes it to turn. If it was parallel at all, if it was anything but at a right angle to the tangential velocity, it would cause it to speed up or slow down, right? Because it would change it in the direction that it is. But as you go in this centripetal acceleration, this centripetal motion, this circular motion, the tangential velocity always stays perpendicular to the center-seeking acceleration, right? So wherever you go, it stays perpendicular. So it never affects the speed. It only affects the direction. It makes it keep turning and makes it keep going around in a circle like this, okay? And what can cause this, we'll talk about that in a few minutes when we get to the next little part, but we can calculate that total acceleration by doing the acceleration, the centripetal acceleration. I don't think you get a C on it in your data booklet, but it's the tangential velocity squared, or the speed squared, over the radius. And so that's our first big equation. That's how we basically define it. V squared over r, however fast this is going over the radius of the circle. If you remember, we can get velocity from angular stuff, so this is dealing with like linear type things. We can make this omega squared r squared over r, which just gives us omega squared r, pretty useful one. But we can also take that a step further, and we can say that omega is 2 pi f, so this is 4 pi squared f squared r. And then here is the other equation that they give you. Frequency is 1 over period, so this is 4 pi squared r over period squared. Okay? Basically just doing some substituting, but they're both centripetal. Again, I don't think the C is on it in your data booklet, but you end up with this, okay? So it's a center-seeking acceleration. It's always pointed towards the center, so it's just always causing it to turn. Just keeps turning, keeps turning toward the center, but never quite getting there. So if we talk now about the centrifugal force, what we want to talk about is what's causing this. So let's talk about centripetal force. I think this was supposed to be an E up here. Centripetal force, okay? And for this is basically the net force on an object. So the net force all adds up, and ultimately is the net force on an object in uniform circular motion, or causing the uniform circular motion. It's pretty simple to get the equation for it. F equals ma. So centripetal force equals mass times centripetal acceleration, which gives us simply centripetal acceleration is mv squared over r. And then you can do the exact same thing as above and make this Fc equals, go through the same steps, just carrying an m along with it, and you'll get 4 pi squared mr over period squared, okay? So those are our equations for centripetal force. Honestly, really the only one you need to know is this guy right here, and if you've got that and you know what omega equals, you know V is omega r, you go through and do that, you've got that. So really you need to know this one, and then this one is just from F equals ma, you just multiply by m, and you've got the centripetal force. So this is the force that's basically causing it to go in uniform circular motion, okay? It's what's giving it that circular motion. And so this is where we start to worry about, like, what's causing it here. So this can be caused by just about any force. So as long as the total net force results in a circular, uniform circular motion or circular path, then we have this centripetal force. Something like gravity can cause it. So let's say we're looking at, here's Earth, and I think I gave this example before, but if we were up on a mountain and we fired something out, right, and we fire it like this, and remember before we fired it, and it kept firing it further and further, and we eventually fired it so hard that it went around the planet and came back to us, and that was in orbit, right? Well, if it's in orbit out here doing that, essentially, what's it doing? It's always being pulled down toward the ground by gravity. There's, its weight, mg, and it's always got this velocity, this tangent velocity as it's moving forward. And the same thing over here. You get right here, tangent velocity, mg, pulling it down, and we've got this centripetal motion going on right here. This motion always, everywhere you go, gravity pointed right towards the center, and perpendicular to that is that tangential velocity as it orbits. So gravity can cause it. Another thing you could imagine is if you were holding a string tied to a ball and you swung this around in a big circle, right? I know my circle, that was really bad. That was a really, 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 really bad circle, but pretend it's a nice, good circle. Let me try that again. So it's probably going to be even worse, but let's say we've got this nice circle, and we have this ball going in a circle. Well, then it would be tension causing it. The ball would be going at a tangential velocity at each point, and the tension in the string at every point. The tension in the string would be pulling it toward the center where you were holding it with your hand as it went around in this circular motion, velocity tangent. But again, the only thing that's causing a force on it is that inward force toward the center, that force from the tension in the string. So it's trying to pull it towards the center, but its velocity perpendicular, that keeps it going on around it. Like how this was falling around the planet. It's like it's pulling in towards the center, but curving away from it all the time. Another thing, it could be friction. So you could imagine you're in a car, and there's a curve in the road, and your car drives along the road, and you manage to make the turn, and there's, it's the friction in your tires. Imagine if there was no friction in your tire, you got up here to this curve, you're on your way to the curve, right? What are you going to do? You're just going to keep going straight. But you're able to turn, which means there's an acceleration, and it's this inward force due to friction in your tires that allows you to turn. So it can be friction. It could be banking. Similar thing, you're going through a turn, but here's a front-on view. The turn is banked, so here's the front view of your car. Headlights, windshield, your tires. The curve could be banked, in which case this normal force here would have a little component pointed inward. So if that was a normal force, if this is theta, we'd have an in cosine theta. We'd have this component here that was pointing inward, and so we could, if this turn here was banked like it is in like in NASCAR races and stuff like that, that can help you turn, and it'll be some friction and some of that banking force, that normal force. And the same thing with like those loop-de-loop tracks where you had like a track that you were sending like a little car on, and it looped around on itself like that, right? Remember those things, loops around on itself, and send the little matchbox car around it, and it goes around the inside and comes out without falling off. Well, this track is providing that normal force, and it makes it go in a loop-de-loop. Same thing for roller coasters that make you turn. The track can provide it. So normal forces again. Even something like a speed bump, you're driving and you go over a speed bump or a hill or something like that, that's circular in nature, make it a big hill. You're driving over it, maybe it's a bridge or something, or even in a short distance, it's a speed bump. That's a terrible car, but you're driving over it, you're going in circular motion, you've got gravity pulling you down. It's a combination of gravity and normal forces making you go in this circular motion. So basically, any time you want to do this problem, you do it exactly the same. You do just what you would do before for net force, except you do net force equals, and instead of MA, well, it's MA, but it's A centripetal. So you add up all the forces, like say it's something like this where you have, it's the car up here. You've got like a normal force pointed down and gravity pointed down, and you add up all the forces acting on it, and its net force equals this. So it's all the forces pointed either directly into or directly away from the center, right? All those center pointing forces, wherever it happens to be, you add up. So you add up all center pointing forces, and you set them equal to, so it's net force equals mv squared over r. And be careful when I say center pointing forces, it can be pointed inward or outward. So like say for example we're going around that loop-de-loop again, like what if you're right here? Well, you have mg down, and you have the normal force pushing perpendicular to the surface, the normal force. So at this point, like you were coming in and going around the loop, if you're at this point in the loop, only this normal force is actually part of the centripetal force. And then the same thing at the bottom. If you're at the bottom, pretend I drew this actually well, and this was straight and flat at the bottom. Let's pretend you're at the bottom of this loop, right? You're at the bottom of this loop. Look, here, so right here, just normal force, but here you have normal force pointed up and you have mg pointed down, right? So these would both count. It would just be n minus mg. So right here it'd just be n equals, so this would be n equals mv squared over r. Down here it would be n minus mg equals mv squared over r. At the top you have normal force and mg pointed down, and it would be n plus mg equals mv squared over r. Okay? So this works for everything. It works for swinging on a swing, pendulum bobs, everything like that. If you look at this, the pendulum, as you swing on this swing, you're sitting here, you're holding on, you're swinging. As you're going through this, try and think about where would be the point where you had the highest centrifugal force. And if you think about it, it's going to be at the bottom. Your radius is the same the whole way because you're on a fixed string, but at the bottom, that's when you're going the fastest. And since this velocity is a part of this, right, this net force is mv squared over r, down here where your velocity is the fastest at the bottom, right, then that's where you have the biggest V, and that's where you have the highest centrifugal force. So if you're ever building a giant swing or something like that, you have to be careful to take this into consideration. So you couldn't just say, well, I need a swing that'll carry me. I'm 150 pounds, so if I get a swing that holds 200 pounds, I'll be safe. Well, the problem with that is when you go on the swing and you're actually swinging, if you swing fast enough down here, it's not just your weight. You have your weight and the centrifugal force all acting on this rope at the moment, kind of like over here, and you've got those both added up, and it can actually end up breaking your rope. So you could be 150 pounds, but if you're going fast enough down here at the bottom, you're going to break that rope. There was that group of people that did that across the Sunshine Skyway Bridge, right? The Sunshine Skyway Bridge, doesn't it look like that? It's got the posts and the different, yeah, like that. And they went up on the old Sunshine Skyway Bridge, and they tried to, it was like 5 of them, they tried to swing down from it on this big pendulum swing, right? It was like a bunch of people, 5 of them all hooked together, and they tried to swing. But the problem is they got a rope that was strong enough just to hold them had they just been sitting there, but they didn't take into account the centrifugal force. So even though the rope could hold their weight, it couldn't hold their weight plus provide the centrifugal force for it, and it snapped. You can look up videos of this and find it of them doing this, and they fell, and they didn't swing and have a nice time. They fell and hit the water, big splash, and some of them got very hurt, I believe, like broken necks and stuff like that. So it's it's a pretty big deal. You got to keep it in mind. All right, I think that's pretty much everything. Oh no, I have one more thing. Was the thing about this is a space station. So if you've ever talked about like general relativity, Einstein said that gravity was an acceleration. And so you could imagine if we did something like this, if we took, and you may have seen this in movies, let's pretend I drew a nice circle here. If we made a circular space station, right, and we set it spinning, and if we could rotate it based on its radius, so based on how big it is, if we rotate it at the right speed, which you could figure out, you could just try it if you want. Say this has a radius of 50 meters or has a radius of 25 meters. How fast would we have to rotate it to get this centrifugal force to equal 9.8? Well, if we did, or I'm sorry, get the centrifugal acceleration to equal 9.8, not the centrifugal force, we could all just walk around the outer edges because you'd be constantly accelerating, and then acceleration, you'd always be accelerating right toward this. So a downward gravity is always equivalent to an upward acceleration, and everywhere you were, the acceleration would be up to you, and we could just walk around this thing, and these upward accelerations to us would feel like these downward gravitational forces, or if there is such a thing, and we could walk around the outer side, and we'd basically have this artificial or have this gravity in space. This is the same sort of thing where if you've ever taken and held like a bucket of water, right, and you're holding on to this bucket of water, right, this is you holding a bucket of water, right, and you've got the bucket of water and it's got water in it, and you take and spin it around in a big circle, right, over your head, and even when the bucket is upside down, right, the water doesn't come out. You're spinning it in this big circle, just like that, around and around, and the water doesn't fall out of it, and it's because of this too, because Einstein said, an acceleration is gravity, and since you are constantly accelerating it toward the center, it's as though there's gravity pointed away from the center. Okay, I think that's pretty much it now for real. All right.